Hello, and welcome to the lecture on heuristic search methods. Your reading is going to be Xiong Chapter 4. So you've up to now only learned how to do pairwise alignments using dynamic programming, whether that be Needleman-Wunsch or Smith-Waterman. And you might think that you could use this method to search entire databases of sequences with many sequences. Well, turns out that this is really not very practical because of the quadratic cost of doing pairwise sequence alignments by dynamic programming. So in this lecture, we're going to cover heuristic search methods, which are going to be a lot faster, but for which there's a bit of a price to be paid in terms of specificity and sensitivity. So we're going to talk about these methods and what their complexity is. How do we define complexity? And we're going to review sensitivity and specificity, and then introduce an older method called FASTA, and the method which has now come to dominate biology, which is BLAST. So first, what is this complexity thing? You've probably already heard this term several times. So in this course, we're going to use the big O notation. And in big O notation, the complexity is defined in terms of a bounding function. So let's say you have this function f of x, and it could be an analytic expression, or it could be even empirical data. But the point is, you have this function and you want to know its complexity. Well, that's going to be given by a function g of x, which should have the property that when it's multiplied by some constant m, it will always be greater than or equal to f of x, as long as x is greater than x naught, right? So if that's the case, then we would say that f of x is big O of g of x, right? And usually you want g of x to be a relatively simple function. So let's say that for your function f of x, you can show that x squared is always going to be greater than or equal to f of x, as long as x is greater than x naught. So if that's the case, then you would say, okay, this function f of x has complexity x squared, or quadratic complexity. Here are a few examples. So let's say your function f of x is just x, like that. So what function can you think of that would always be greater than or equal to x? Well, this was easy. You can just say x, right? This x is actually exactly equal to your original function, right? So it's your m times x would meet these properties, right? And in fact, in this case, x naught could just be minus infinity. Oops. So simple enough. Let's try a slightly harder case. So let's say your function f of x is x plus x squared. So what does that look like? Probably something like this. Okay. In the case of a sum, your complexity is going to be given by the highest order term, right? So in this case, x squared, and you can just ignore all the other terms. That's a quick shortcut. So that means that just by inspection, we could say, okay, then the complexity is big O of x squared. So that means that if I draw a function like this, m times x squared, there's some function, there's some m for which m times x squared will be greater than or equal to x plus x squared for all x greater than x naught. Okay, so then we would say that this is complexity big O of x squared, right? So what about this third function, x times sine of x? So x times sine of x, sine of x varies from -1 to +1. And so this x that's multiplying it by it should just be some sort of bounding function that looks like that. You know, and so x times sine of x would look kind of like this. Okay. And so a function that's always greater than or equal to this function for all x greater than x naught could be just m times x. See that? Where m could just be unity in this case. So in this case, your x naught would be 0. Okay. So then that would be big O of x. And x times sine of x is not a terribly good example because it becomes negative for over half its range. But it gives you the idea of how to apply this definition of big O notation. Okay, so what about sensitivity and specificity? So you probably have seen this before, so hopefully this is just a review. But let's say you have some test. It could be a diagnostic for COVID-19. And this test returns some sort of score. And you want to know how you want to characterize this test. So you get together a group of people that you know are sick with COVID. You know because you tested them by some high confidence method. And this would be your gold standard positives. Gold standard positives. Right. So you can see that some of these sick people would get a high score on your diagnostic test. So maybe that's working well, but some people would get a low score. Then you would have your gold standard negatives. And these are people that you know to be healthy. So you can see that there's a bit of a problem here because some of the healthy people would get a high score on this test. So they could easily be confused for sick people, or they would be confused for sick people. We call those false positives, or FP. And that depends on your choice of threshold. This is your threshold. And when some test gives you some continuous result, then you're free to choose whatever threshold you want. And likewise, the gold standard positives, there are some of them, those below this threshold, who would be diagnosed as healthy when they're actually sick. And those we call false negatives. Okay? And the sick people who test sick, those are true positives. And the sick people who test sorry, I don't know if I said this correctly. The sick people who test positive, those are true positives. The healthy people who tested negative, those are true negatives, right? So TN is everything under this curve, the gold standard negative curve, but to the left of the threshold. Okay. So sensitivity means how many of these gold standard positives was your test able to detect, right? And just so it's easier to remember, just try to think that sensitivity is all about the gold standard positives. It doesn't include anything having to do with the gold standard negatives, right? So sensitivity sensitivity is true positives divided by true positives plus false negatives, right? Basically, out of this curve, the gold standard positives curve, how many of the true positives were you able to detect as a function of divided by the total area under this curve? And then specificity is kind of the converse or the dual of this. That's how many of the gold standard negatives were true negatives. So that's true negatives divided by true negatives plus false positives. Okay, and again, so it's easier to remember. The specificity has to do only with the gold standard negative curve. So Tn is the area under the gold standard negative curve to the left of the threshold, and Fp is to the right of the threshold. Let's do the same curve. Okay, and so you can actually vary this threshold. You can move it to left, and that means that you'll get more test positives. But of course, a lot of those will be false positives, right? So we call that a loose criterion. You can also move it to the right, and then you'll have the opposite problem, where now you will have everything that your gold standard negatives will be true negatives, but then you'll also have some false negatives. So some of your sick people will be misdiagnosed as healthy, and so we call that a stringent criterion if you move the threshold to the right. And you can actually one very convenient way to do this to sort of summarize these results is to plot sensitivity and specificity for every possible value of the threshold, from the most negative to the most positive, in a single curve called a rock curve, right? So you just draw a curve of, you have sensitivity and specificity on the two axes, and you just draw the curve over all thresholds. But we don't need to get into that right now. So why do we need heuristic search methods? And as I mentioned at the beginning, it has to do with the speed or with the cost of doing pairwise alignment, which would have been otherwise been the most obvious way to do a sequence search. So the pairwise sequence alignment has a cost that goes like n squared, and the reason it's n squared is because if you think of both the query and the subject sequence as both having length n, then you would have to fill in this alignment matrix, which has size n by n, right? So n squared. And you still have to also do the traceback, but the traceback is less than a quadratic operation. So it's going to be driven by this matrix filling step. And that might be okay if you're doing a pairwise alignment, even for a very long sequence, right? When it starts to not be so acceptable is when you have to do that pairwise alignment for an entire database of maybe 100 million sequences. So that's where the heuristic methods come in. They're not intended to be as sensitive or as specific as Needleman-Wunsch or Smith-Waterman, but they're a lot faster. So an early method to do this was called FASTA, and the way it works is it creates a hash table with all occurrences of each amino acid, each of the 20 amino acids, both in the query and the database. So doing this in the query wouldn't take very much time, but doing this over an entire database, again, of hundreds of millions of sequences, that could take quite some time. But you only have to do it once, right? And then the database just has this index, and maybe you have to update it every time experimentalists upload more sequences. But it's not something that has to be calculated every time a user wants to do a search. So you have this hash table where you know where each amino acid type occurred in the query sequence and everywhere in the database. And then you start making lists of pairs of occurrences. Like let's say alanine occurred at position 1 in the query and at position 15 in the database, right? So you have this 1 and this 15, and they're offset, the difference between those two. So in this case, 14. And you would do this for all 20 amino acid types. And then what you do is you would sort by the offset. So that what that would end up doing is that all the times that you see a single amino acid occurring at a set offset, like let's say every time it occurred at offset of 14, these would all be together on your list. And so you could group them into this thing called a K-tup. And you can think of this as a diagonal in this gigantic alignment matrix. And then you can start doing some joining. Like you have a bunch of big diagonals, and you'll find that it's at this point relatively cheap to join them, because you're no longer going to have to be doing dynamic programming over the entire sequence. You're just talking about a little section of your alignment matrix that's defined by the ends of these diagonals. So this is sort of what this hash table would look like. Let's say this is your query sequence, and you have an alanine at position 1, right? And then in your database or your subject sequence, you have an alanine at position 6. So the offset is 6 minus 1, or 5. Then your G, that occurs in your query at position 6, and your database at position 1. So here you have an offset of minus 5. Then you have S, occurs at position 4 and 3, and so that gives you an offset of minus 1. And there's a D that occurs at 5 and 4, so again gives you an offset of minus 1. And let's skip down here to the P, and the P occurs at positions 3 and 2, right? So you can already see that I managed to align sort of these 3 residues. And that's easy enough for us to see it visually. But the way it would actually be implemented is we would sort this list by offset. And that way this P, S, and D would be together on this list, and it'd be a K-tup of 3 residues. So here you'd have this sort operation, but sorts are not quadratic, right? It depends on what kind of sort you're doing, but it's going to be much better than quadratic. Right, so here are the 3 residues that matched. And once you have these K-tups, you can think of them as being like these diagonals. You can start eliminating some of them. Like you can make these boundaries that define a band or about the diagonal. Anything that's outside of that band, you can just throw away, right? And then you can also do things like throw away the diagonals that are too small. And so maybe that would get rid of this one, maybe that would get rid of this one. And that would leave you with a relatively limited number of diagonals. And there would not be all that many ways to connect them, right? And once you go decide which way you want to connect them, then actually drawing this traceback, or actually I should have done like this, is a relatively easy problem, because you're talking about a very tiny submatrix of your alignment matrix. So this might be dynamic programming, but it's over a much smaller domain. Okay, and one other thing that we have to consider after we've done alignment is how to determine the significance of that alignment, because two sequences that might align over some fragment, if you do this enough time, this is something that could happen just by chance, right? So what people have come up with is this idea of using this Gumbel extreme value distribution to try to determine the significance. So we're namely the p-value. So what we're going to do is we're going to take one of our 2 sequences and we're going to scramble it, right? And then we're going to try the alignment again. and calculate the score, and scramble it again and calculate the score, and scramble it again and calculate the score. And if you do that, it turns out that you get this thing called the Gumbel extreme value distribution, and this will have some peak at some score, right? There's some scores that there are very many ways to get a score like this. There are a comparatively small number of ways to get a high score, right? And likewise, and perhaps surprisingly, there are surprisingly small number of ways to get a very, very low score. Because when you think about it, there are only 20 amino acid types. So these very low scores, which mean that you went through the whole sequence, but you were hardly able to align anything. Like you were there, that seems actually kind of unlikely. Because if your sequence has length of 100 or 1,000 or something like that, there should be plenty of opportunities for at least short segments to align between the two sequences. So what you do is you get the score that you actually got from your original sequence, and calculate the area under the curve to the right of that score. And so that's the probability of getting that score or higher. And we call that a p-value, right? So this area divided by the total area is your p-value. The total area should be 1 because of the probability distribution. So what's the Gumbel extreme value distribution? Well, we're not going to derive it, but it's something that was developed to compute the probability of extreme events. So for example, let's say our extreme event is flooding in New Orleans here in Louisiana. So New Orleans is at the mouth of the Mississippi River, which drains a gigantic area, right? So let's say some of the tributaries of the Mississippi might originate, like let's say one in Iowa, one in Ohio, one in Illinois, I don't know, one in Kansas, and so on. And it turns out if we have a huge rainstorm, let's say here in Ohio, then maybe you get flooding in Ohio. But by the time you get down here to New Orleans, maybe the effect would be rather minimal because the Mississippi is a very big river. Maybe you can absorb that much rain. Okay, so let's say you have two extreme events. Let's say there's also a big rainstorm here in Iowa. Maybe you start to see a little bit more effect in New Orleans, but still not what you would consider an extreme flood, right? But then let's say you get another big rainstorm in Kansas. Okay, 3 extreme events. That might be enough to where now you get flooding down here in New Orleans. And so if you think about it, the probability that any two residues will be the same type, well, it depends on the frequency of that type. But let's just say, for the sake of argument, that all amino acids have the same frequency of 1/20, then there would be a chance of 1 in 20 that they would be the same type, right? And you might say, okay, 1 in 20, that's not terribly likely, but then again, we have lots of residues in our sequence, so there are lots of opportunities for that to happen. So maybe that's not so significant. And then you say, okay, but then if it's alanine followed by lysine, the probability of those two occurring together, maybe 1 in 400. But again, we still have a lot of residues in our sequence in our database. Maybe 3, 4, 5, at some number of residues, you might say, okay, well, this is starting to get to be something where it's not likely to have occurred by chance. Like it's indicating some common ancestry. And so this is very kind of analogous to this other problem of flooding in New Orleans, in that you had to have a certain number of extreme events happening before this sort of bigger downstream event could be said to exist, right? So the Gumbel extreme value distribution is what you're going to do to calculate your p-value, or the significance of a given match score. Now we're going to talk about the successor method to FASTA. It's called BLAST, which you all surely know by now. And it's very similar, except this hash table, instead of using single amino acids, it has so-called 3 residue words. And then what you're going to do is you're still going to find these k-tuples, like multiple words with the same offset. And then you're going to extend them to left and right, perhaps a bit more permissively, like you'd allow it to extend as long as their similarity maybe not necessarily sequence identity. And then you would collect the best matches, and again, you would use as a seed for gapped alignment. So that's kind of what it looked like. Let's say this is your query sequence. And this is your database with your subject sequence 1, and then maybe there's a sequence 2, and then a sequence 3, and so on. And these k-tups would look kind of like this. These are places where you got, let's say, 4 words in a row that are matched between the query sequence and the subject sequence. And let's say in the sequence 1, you would get these 3 like that. And sequence 2, you get a couple. And sequence 3, maybe there would also be a couple. And then you would do this match extension. And that means, again, you extend left and right. And you find that, okay, it's not just the original 4 words, but there are also adjacent residues that match to some degree. And you can extend it like this until you start not matching anymore, right? And then now your match is longer. And the same thing happens for all of these, right? And the same thing could happen here for sequence 2 and sequence 3 and so on. And then you could apply some algorithm where you do things like throw away the small diagonals, ignore anything that's kind of far from the diagonal, from a banded diagonal, and then start connecting these hopefully small remaining gaps. And again, this is a gapped alignment, but it's done over a very restricted domain, so it's really fast. And the number of these possible gapped alignments is also small because, again, we throw away the smaller hits. And so you can see that here we got a nice long gapped alignment, and then for sequence 2, there's also a nice long gapped alignment, and so on. Okay, and there's one thing that you have to keep in mind, is that there are these so-called low complexity regions. And what do we mean by low complexity? We basically anything that might have maybe a significant length, but not very significant complexity or information. And in this case, the kind of complexity we're talking about is best, in my opinion, described by the Kolmogorov complexity. Let's say Kolmogorov complexity. And so what Kolmogorov did was he said that the complexity of a given string is given by the length of the smallest program that could reproduce that string, right? So let's say you have 100 residues and they're random. Then your smallest program that could present this string is perhaps 100 characters long. But if your residues are repetitive, like let's say just a bunch of A's, then you can imagine that you could invent some syntax where it's like your string that's repeated, and then some kind of multiplication operator and the number of times that this appears, right? A times 100, that could be expanded out to A 100 times. And so the Kolmogorov complexity of the string would then be 5, right? Not 100. And the same way, if you could have some string that's like several residues that just keep repeating ALK, ALK, ALK for a whole bunch of times, maybe that would be described as ALK times whatever number of times that appears, right? And so this program would only include 1, 2, 3, 4, 5, 6 characters, right? So you say, oh, Kolmogorov complexity of 6. So the point is that these low complexity regions exist in genomes. They are about 15% of public databases, and you could get hits. You could get reasonably high scoring alignments to them, but that doesn't reflect common ancestry. so you should consider them to be spurious. And there are programs to do this, and they've already been implemented on the BLAST server. So when you do a BLAST search, these are filtered out automatically. Okay, so we said the p-value gives this likelihood of a single hit occurring by chance. But we also talked about this idea that you get more than one chance to make this hit, and so you have to take that into account. And so the number of like the probability of hit times the number of opportunities you had to get that hit is called your e-value, or your expectation value. E is expectation. Okay. So p-value can be computed a number of ways. We talked about one way. One way that I find really informative is if your scoring is done using a bit score, because bits are a very easy to use fundamental unit of information, and it's I find that there's the most intuitive way to sort of quantify information. For instance, let's say I flip a coin, and I tell you the results of that coin flip. You might ask the question, what is that information worth to you? Well, there are two possibilities, and if it's a fair coin, then each of those possibilities has probability of 50%, right? So your p-value, or your probability of a certain event happening, or probability of correctly guessing a certain event, would be 1 over 2 to the s prime, where s prime is your bit score, right? And we said it was 1 bit. So in this case, that was 1 over 5. Well, sorry, 1 over 2. Right. But what if I flipped a coin twice and give you the results of both of those? Well, then that is worth 2 bits to you, right? Because there's 1 bit for one and 1 bit for the other. And so now the p-value of that is 2 to the 2. So if I guess both of those correctly, you would say, okay, well, p-value for that is 0.25, right? So still something could have happened by guessing. Then likewise, if I flipped the coin 3 times and told you the result 3 times, and either guessed or just told you what the result was and it was correct, then that would have a p-value of 2 to the 3, right? So 1/8. But the issue is that that you also have to take into account how many opportunities you gave me, right? So if you say, okay, flip the coin 3 times and tell me and guess the results in advance, and I got it right, well, that seems kind of remarkable, because there's only 1 in 8 chance of that happening randomly. But what if you gave me 8 opportunities to do this, and I got it exactly right only once? Well, then you would say, well, each time he had a 1 in 8 chance of getting it right, but he had 8 chances. So my expectation is that he would have gotten it right once if you were just guessing. And so that's what the expectation value is. It's basically p-value times the number of opportunities. And so in the case of a database search, your p-value, if you're using this bit score, would be again 1 over 2 to the s prime. But you multiply that times the sequence length and the database size. So database size, it's easy to see that you should do that, because however long your string is, the starting point could have been at any residue in this database, right? And then likewise, your partial matches are allowed, right? So within your query, the partial match could have started in principle any residue in your sequence, and that's why you also have n. So the expectation value is mn times p, right? Right. And I'm using bit scores, whereas your sequence alignments will give you some sort of raw score. There's always going to be some way to convert this raw score to this bit score, right? The raw score might not be in bits. In fact, in general, it's not. But the main matrices PAM and Blossom are formulated in such a way that you could back out that you could easily figure out how to convert these to bit score. And we're not going to go through that exercise because it's mostly just tedious algebra. Or I mean, not even all that tedious, but it's not a threshold concept. I think it's enough just to describe how to do it given a bit score. And that's all I wanted to say for about heuristic search methods. Thank you very much, and I'll see you at the discussion section.